In quantum field theory, a fermionic field is a quantum field whose quanta are fermions, that is, they obey Fermi-Dirac statistics. Fermionic fields obey canonical anti-commutation relations rather than the canonical commutation relations of bosonic fields. The most prominent example of a fermionic field is the Dirac field, which describes fermions with spin 1/2. Electrons, protons, quarks, etc. The Dirac field can be described as either a 4-component spin or as a pair of 2-component WEYL spinors. Spin 1/2 Majorana fermions, such as the hypothetical neutralino, can be described as either a dependent 4-component Majorana spin or a single 2-component WEYL spin. It is not known whether the neutrino is a Majorana fermion or a Dirac fermion. Basic properties. Free fermionic fields obey canonical anti-commutation relations, i.e., involve the anti-commutators A, B equals AB plus bar rather than the commutators A, B equals AB minus bar of bosonic or standard quantum mechanics. Those relations also hold for interacting fermionic fields in the interaction picture, where the fields evolve in time as if free and the effects of the interaction are encoded in the evolution of the states. It is these anti-commutation relations that imply Fermi-Dirac statistics for the field quanta. They also result in the Pauli exclusion principle. Two fermionic particles cannot occupy the same state at the same time. Dirac fields. The prominent example of a spin 1/2 fermion field is the Dirac field, and denoted by the equation of motion for a free field is the Dirac equation, where a gamma matrices n is the mass. The simplest possible solutions to this equation are plane wave solutions, and these plane wave solutions form a basis for the Fourier components of, allowing for the general expansion of the Dirac field as follows. U and V are spinors, labeled by spin. For the electron, a spin 1/2 particle, S equals plus 1/2 or S equals minus 1/2. The energy factor is the result of having a Lorentz invariant integration measure. Since can be thought of as an operator, the coefficients of its Fourier modes must be operators too, hence, and are operators. The properties of these operators can be discerned from the properties of the field, and obey the anti-commutation relations, where A and B are spin or indices. We impose an anti-commutator relation in order to make the operators compatible with Fermi-Dirac statistics. By putting in the expansions from the anti-commutation relations for the coefficients can be computed in a manner analogous to non-relativistic annihilation and creation operators and their commutators. These algebras lead to the physical interpretation that creates a fermion of momentum p and spin s, and creates an antifermion of momentum q and spin r. The general field is now seen to be a weighted summation over all possible spins and momenta for creating fermions and antifermions. Its conjugate field is the opposite, a weighted summation over all possible spins and momenta for annihilating fermions and antifermions. With the field modes understood and the conjugate field defined, it is possible to construct Lorentz invariant quantities for fermionic fields. The simplest is the quantity. This makes the reason for the choice of clear. This is because the general Lorentz transform on psi is not unitary, so the quantity would not be invariant under such transforms. So the inclusion of is to correct for this. The other possible non-zero Lorentz invariant quantity, up to an overall conjugation, constructible from the fermionic fields is, since linear combinations of these quantities are also Lorentz invariant. This leads naturally to the Lagrangian density for the Dirac field by the requirement that the Euler-Lagrange equation of the system recover the Dirac equation. Such an expression has its indices suppressed. When reintroduced, the full expression is the Hamiltonian density can also be constructed by first defining the momentum canonically conjugate to, called with that definition of the Hamiltonian density is, whereas the standard gradient of the space-like coordinates, and is a vector of the space-like matrices. It is surprising that the Hamiltonian density doesn't depend on the time derivative of directly, but the expression is correct. Given the expression for, we can construct the Feynman propagator for the fermion field. We define the time-ordered product for fermions with a minus sign due to their anti-commuting nature, plugging our plane wave expansion for the fermion field into the above equation yields, where we have employed the Feynman slash notation. This result makes sense since the factor is just the inverse of the operator acting on in the Dirac equation. Note that the Feynman propagator for the Klein-Gordon field has this same property. Since all reasonable observables are built out of an even number of fermion fields, the commutation relation vanishes between any two observables at space-time points outside the light cone. As we know from elementary quantum mechanics, two simultaneously commuting observables can be measured simultaneously. We have therefore correctly implemented Lorentz invariance for the Dirac field, and preserved causality. More complicated field theories involving interactions can be analyzed too, by various perturbative and non-perturbative methods. Dirac fields are an important ingredient of the Standard Model.